Here's the dilemma. We know how to get to relativistic speeds in laboratory. We do it all the time. And then we go to the macroscopic level where things like aircraft, cars, spacecraft were pathetically slow. So the question is, can we bridge that gap between what we do now on the macroscopic level with chemical binding energies to relativistic speeds, which are done with electromagnetic acceleration? The shuttle, when it would take off, or the SLS, when it will take off, will have a power off the launch pad of between 50 and 100 gigawatts. Turns out, to get to relativistic speeds with the spacecraft we're talking about, you need basically the same power level. And for about the same amount of time. It takes 10 minutes to get to orbit with the shuttle. It takes us 10 minutes to get to 30% the speed of light with about the same power level, just using different technology. We could propel a 100-kilogram robotic craft to Mars in a few days. If you want to push something like shuttle class, it takes you roughly a month to get there. Within about 25 light years of the Earth, there's actually quite a few potential exoplanets and habitable things to visit that may be habitable. We don't know, of course. And so there are many targets to choose from. The closest is Alpha Centauri, which is about 4 light years away. So photon-driven propulsion is not a new idea. It goes back to the beginnings of thinking about light in both the classical and the quantum mechanical way. There are recent advances which take this from science fiction to science reality. There is no known reason why we cannot do this. There's a roadmap, which you can look at in our paper, to relativistic flight. The system is completely scalable modular. Build any size you want, from a tiny one to a gigantic one.